Welcome to session 3 of module 1. In the previous session, that is session 2, we had derived an expression for the allowable stresses in concrete dam. That is expression for P max and P minimum at the toe and heel. So in this class, we'll learn how to find the principal stresses, because this is not the maximum stress. Whatever we have derived is not the maximum stress acting on the dam. So we have to derive the expression for principal stress. So let me share the content. Principal stresses and shear stresses. So normal stresses on the horizontal plane. For the normal stresses at heel and toe, we have found the expression. So P maximum is at the toe, that is you have to use a plus for that, and P minimum is at the heel, you have to use a minus symbol for that. So sigma V is the sum of all the vertical forces, B is the base width of the dam, and E is the eccentricity of the resultant force, which should pass through the middle third for no tension to develop. And again, this is eccentricity of the resultant force from the center of the base, which is given by net moment divided by net of vertical forces, that is sigma h, and this is sigma m, net moment. Net moment is nothing but the difference between the overturning moment and the resisting moment, sigma r minus sigma m naught, if you take moment about the toe. So we will work a numerical problem on this, so you will understand it better. So sigma v is the total vertical force and B is the base width of the dam. So we should see that when the dam is full, when the reservoir is full, the resultant will be towards the toe, because sigma h will be more. This is when the reservoir is empty, the resultant will be towards the heel, because sigma h will be less compared to this case. Okay, because the reservoir is empty, there is no major horizontal force from the water. Okay, vertical stress intensity determined from the equation which was shown in the previous slide is not maximum stress produced in the dam. It is not the maximum stress produced in the dam. So maximum normal stress will be the major principal stress which is generated on the major principal plane. So we have to determine the maximum principal stress, which has to be found out. Okay, so for that we will consider a small element at the toe. This is the small element A, B, C, which is considered near the toe, and you can see there are three faces, A, B, B, C and CA, which are subjected to the stresses. So this AB is subjected to a stress P dash, which is because of this tail water on the downstream side, and this for face AC is subjected to uplift pressure PV, which is from the bottom of the dam, and this face BC is subjected to sigma. This is sigma, which is normal to this plane. Okay, that is because of the water pressure. So these are the three different phases subjected to different intensity of stresses. One is P dash, the other one is PV, and the other one is P or sigma. So let us enlarge this small element and see how it looks. So this is the phase AC, which is at the bottom. So where the stress intensity is PV, that is because of the uplift pressure, and this is AB. I've taken the length of that element as length of that phase as ds, and here the stress intensity is P dash, that is because of the tail water, and this is BC, which is due to because of this there is sigma, this is because of the water, and the length is dr. Let alpha be this angle, and this is 90 degrees. So ABC is the enlarged triangle of the small element which we have considered near the toe. So this pressure is converted to force here. This pressure is converted into force. What is force? Force is stress into area. So for analysis, we always consider the unit length of the dam. So unit length of the dam is 1 meter. So therefore it is sigma is the stress here. Sigma into this length dr is the force here into 1. 1 is the width of the dam or the length of the dam which you are taking in the other direction. So what is the force here on this face BC is sigma into dr, which will be acting at the center. And ds is the length of AB. So intensity of pressure is P dash. P dash stress into area, ds into 1. That gives the force here on the face AB. And similarly, there is this force, uplift force, that is PV multiplied by this length dB. So here the stresses are converted to forces. Stresses are converted to forces. So dB is the length, ds is the length, and dr is the length here. Sigma dr is the force here. P dash ds is the force here. PV dB is the force. Along with this normal forces, the forces which are acting perpendicular to the faces, there is this shear stress at the bottom, that is near the foundation, that is acting parallel to the plane. This is denoted as toe. This is denoted as toe. Shear stress is toe. And the shear force can be toe into dB. Toe into dB. This is along the length AC. The length AC is nothing but dB. So this is the enlarged portion. So now we for finding out this sigma and toe, we have to find out the sigma, the principal stress, and toe, the shear stress. Therefore, we are resolving these forces into horizontal and vertical direction. These are the inclined forces. So this is a vertical force, no need to resolve, and this is a horizontal force, no need to resolve. This is sigma dr. So where is the what is this angle alpha? This angle is taken as alpha. This is 90 degrees. This is 90 degrees. The angle between the face AB and BC is 90 degrees. So this is your adjacent side. This is your hypotenuse, and this is opposite for this alpha. Okay. So when this is alpha, this angle with the vertical is 90 minus alpha. If you complete this triangle, this angle is 90. This angle is 90 minus alpha. So 90 minus alpha plus 90, the total sum of all the angles should be 180 degrees. So this will be alpha. So this will be alpha. So this is 90. This is 90 minus alpha. If you draw vertical here, it will be 90 minus alpha. 90 minus alpha plus 90. So the remaining angle is alpha. Similarly here. So here, this is alpha. Alpha with respect to vertical, because this is 90 minus alpha. This is alpha. This is 90. This is 90 minus alpha. 90 minus alpha minus 90. So this will be alpha. So this is alpha. So therefore this is 90 degrees. This will be 90 minus alpha. And the remaining angle is 90 minus of 90 minus alpha, which is equal to alpha. So these are the angles. So knowing this angle, so the horizontal component here will be sigma dr sine alpha, and the adjacent one is here sigma dr cos alpha. So here this will be sine and this will be cos. So now we will take up and we have to find out this value of sigma, the principal stress, and the shear stress. So for that, let us take up sum of all the vertical forces. The same diagram I have taken here. So sum of all the vertical forces. So this is sig PV into dB, which is acting vertically upward. So I have taken positive, minus of sigma dr cos alpha, which is negative because it is acting downwards, and another vertical force is P dash ds sine alpha, which is acting vertically downwards. So sigma is equal to, you can take out this sigma, we want sigma, principal stress. So if you take out sigma, it will be PV into dB minus of P dash ds sine alpha divided by dr cos alpha. Okay, this expression by simplification of this equation you will get. Then from the triangle A, B and C, you can see that this sine alpha is opposite side by adjacent side, which is equal to AB, sorry, opposite side by hypotenuse, AB divided by AC. AB is nothing but length ds, ds divided by dB. Similarly, cos alpha is adjacent side, this length is dr, dr divided by hypotenuse dB. So dr by dB, or from this you can write, we want expressions for ds and dr, we want to substitute in this equation. So ds is equal to dB sine alpha, and dr is equal to dB cos alpha. You will get these two from these two expressions. Substituting the above equation, this is equation 1. From this equation 1, sigma is equal to PV dB minus of P dash in ds sine alpha divided by dr cos alpha. For ds I am substituting it as dB sine alpha. For dr I am substituting as dB cos alpha. So here cos alpha is existing earlier, so it will be cos squared alpha. So taking out the terms independently, dB dB get cancelled. So it is PV cos square alpha minus of, here sine alpha will be sine square alpha divided by cos square alpha. We can write sine square alpha by cos square alpha as tan square alpha, and 1 by cos square alpha as secant square alpha. So this is the expression for the principal stress. So sigma is equal to PV secant square alpha minus P dash tan square alpha. So if we want the maximum stress, when will be the stress maximum? When this term is 0. When this term is 0 means P dash should be 0. What is P dash? P dash is the force due to tailwater. So if there is no tailwater in the dam on the downstream side, so sigma will be PV secant square alpha. PV secant square alpha. If hydrodynamic pressure PE dash is considered, hydrodynamic pressure is due to earthquake pressure in the water. So therefore that will be you have to subtract that force near the toe and add that force near the toe. So adding considering that, the sigma at toe will be PV secant square alpha minus of P dash minus P dash E tan squared alpha. Substituting in the previous equation, that is this equation, substituting in this, adding that P dash, PE dash is the hydrodynamic force. So this is what you get for sigma at toe and sigma at heel. So to find out the shear stress toe, let us take sigma h is equal to 0. That is sum of all the horizontal forces is equal to 0. That is considering the forces acting on the small element. So here toe dB is horizontal, which is from right to left. This is taken as positive. So these will be negative. So minus of dr sine alpha here, and this will be again positive, minus of P dash ds cos alpha. Or we want the expression for toe. So toe is equal to these two divided by dB. So we already know that ds is equal to dB sine alpha and dr is equal to dB cos alpha from the triangle ABC. So substituting that here, one second, let me go to the previous slide. So substituting that here, so dr is substituted as dB, and ds is also substituted in terms of dB. So dB will be taken out as a common term and it will be cancelled. So if you cancel dB, this is the expression you will get, sigma minus P dash sine alpha cos alpha. We know that sigma stress, we have already determined the expression for sigma, that is the principal stress, that is PV secant square alpha minus of P dash tan square alpha. So substituting this in this expression, so toe will be equal to, for substituting for sigma, PV secant square alpha minus of P dash tan square alpha minus of P dash, this P dash, sine square tan square, that this is substituted. Here you have sine alpha cos alpha, sine alpha cos alpha, and then here PV secant square alpha minus of P dash tan square alpha plus 1, taking out P dash as common. So that is written as PV minus of P dash tan square plus 1 is secant square alpha. Secant square alpha is taken as common, secant square alpha into sine alpha cos alpha. Secant square alpha is written as 1 over cos square alpha. Cos alpha get cancelled. Sin alpha divided by cos alpha will be tan alpha. So it is PV minus P dash tan alpha. If there is no tail water, that is P dash is 0. So it is PV tan alpha. Tau is equal to PV tan alpha. If hydrodynamic force is considered, same way at the toe it is P dash minus P dash E tan alpha, and PV minus P dash plus P dash E tan alpha is at the heel. These are the expressions we are going to use to determine the shear stresses at the toe and at the heel, and also the norm this thing direct stresses, sigma principal stress and the shear stress, and we also know how to find out the normal stresses. So thank you.